If we can talk about derivatives of vector-valued functions, then maybe we want to talk about also integrals of vector-valued functions. So let's remind ourselves what an integral is. So if we take an interval, that interval is going to be between, say, a and b, and we're going to divide it up into pieces. Each of those segments will have a length of delta t being b minus a divided by the n segments that we divide the interval up into. And then we'll label these points. We'll call them t sub 0, t sub 1, t sub 2, all the way down to t sub n. And in each one of those sub-intervals, say tk minus 1 to tk, we will choose a point called tk star. So each one of these intervals has a point tk star, and they don't have to necessarily be at the same point of that interval. Then when we want to define the integral, what we're going to do is we want to sum our function f evaluated at that tk star times delta t. So we're going to sum that from k equals 1 to n. But if we want, that's just a Riemann sum. If we want that to be an integral, we're going to want to take the limit as n goes to infinity. Of course, that will let delta t go to 0. And these sums, we've interpreted them as area under the curve. But also we can think about them as accumulated rates of change or net change. That net change interpretation works really well when we're talking about the fundamental theorem of calculus. That theorem says that if our function f is continuous and we have an antiderivative, capital F, then we can evaluate the integral by taking the antiderivative, evaluating it at b, and evaluating the antiderivative at a, and subtracting them. And so the fundamental theorem of calculus really says that the integral is the net change of the antiderivative from a to b. Now we want to extend that definition to vector-valued functions. So I want to do the integral of r of t from a to b. So I'm going to use that same definition, the limit as n goes to infinity, of the sum from n equals 1 to infinity of r of tk star delta t. But then I'm going to write that in components. So that's really the limit as n goes to infinity of the sum from n equals 1 to infinity of f of tk star delta t, and then the sum from n equals 1 to infinity of g of tk star delta t, and the sum from n equals 1 to infinity of h of tk star delta t. And so really, if we take the limit as n goes to infinity of each one of these components, we get the integral of each one of these components. The integral of f of t dt, the integral of g of t dt, and the integral of h of t dt. So the integral of a vector-valued function, r of t, is just the integral of each of the component functions. And we can have a fundamental theorem. If we have an antiderivative, capital R, of our vector value function, little r, then we can find the integral by evaluating that antiderivative at b, and then subtracting the antiderivative at a. So now how do we interpret this new integral that we found? Well, this is not the area under the curve. Not at least in the way that we thought about it before. If you think about an object like that helix that we looked at earlier, then you would see if we looked at the area under the helix that some of those areas would start to overlap, and area under the curve just really isn't a great interpretation for this integral. We should really think about it more as accumulated rates of change, okay, or maybe some sort of net change. Or another way to think about it is we know that the derivative of position is velocity, so maybe the integral of velocity, well, it's not position, but it's the net change of position or displacement. So think about displacement as net change of position. Okay, so let's do one last example. Suppose that a moving point or object has a given initial position vector r of 0, which is 2I. And it has an initial velocity vector v of 0, which is I minus j. And finally, we define the acceleration vector to be 2I plus 6tj. Now we want to find the position and velocity vectors given that we know the acceleration. So we know acceleration. Acceleration is going to be 2, 6t if we want to write it as a vector instead of the components I and j. And if we want to find the velocity, well, we just take the antiderivative of acceleration. We could take the antiderivative of acceleration, so we could write it as 2t plus a constant, 3t squared plus a different constant, maybe I'll call that d. And then we could solve for c and d knowing that we know the initial velocity. I'd like to actually write this a different way using the fundamental theorem of calculus. If the antiderivative of acceleration is velocity, I can write that general antiderivative as v of 0 plus the integral from 0 to t of the acceleration vector a of s ds. So that initial velocity is 1, negative 1, plus, now I'm going to do the integral from 0 to t of 2 and 6s ds. So that's going to be 1, negative 1, plus, this integral will be that one that we saw before, 2t and 3t squared. Okay, so my velocity is going to be 1 plus 2t and negative 1 plus 3t squared. Now, the antiderivative velocity is going to be position. So I can write the position vector as being r of 0 plus the integral from 0 to t of v of s ds. So r of 0 was given to us. It is 1, No, it is 2, 0. And we want to integrate our new velocity vector, which is 1 plus 2t, or 2s in this case, negative 1 plus 3s squared ds. So we're going to get 2, 0. And then if we integrate each one of these components, we should get t plus t squared and negative t plus t cubed. And so our new position vector is going to be 2 plus t squared, just adding the components, and negative t plus t cubed. And that is an example of how we can start with an acceleration and use that to integrate and get a velocity vector, and then use that to integrate and get a position vector.